Um, oh no, Maxime is coming. So nice afternoon to you all. I'm Antoine Chambert. So we'll do classes about how can we do elementary number theory in Lim. And by elementary, it means it will really be elementary, essentially integers and stuff like that, and not complicate the stuff with integers, but really. So I have only two parts for today, and then we'll have experiments. So we want to do elementary mathematics in Lim. So I repeat, and so I hope that you will be able to enlarge your mathematical knowledge, but that should be only moderate because we'll do elementary stuff. And more significantly, your ability to write mathematical proofs in Lim. And for us, and for me at least, I view this as a crash test. I mean, if something is not easy, if something that is mathematically easy is not easy to do in Lim, it means that there is for the moment a problem somewhere in the building of the system. So, and there are these three books that we will roughly follow. And this morning we have seen Alex talking about principles of mathematical analysis. And I'll do the classical introduction to modern theory by Ivan Rosen. And I think Heather is going to use the book of Byrne. So there are many issues that we will encounter. I say may, but certainly we will. So first is finding the math behind the mathematical statement. How do we prove this? But elementary math means that probably that part is not too difficult. Then finding the idiomatic way to phrase mathematical results in Lim or Mathlib. And sometimes there are different ways. It might be equivalent. It might be not. It might be not equally practical while mathematically equivalent. So we'll have to search within many typos, I'm sorry, within the documentation of the Mathlib library and crying that things would be easier if Mathlib had some lemma which isn't there, and dreaming that things would be even easier if the machine had some algorithm to do the job for us. So your hopes and mine will differ. Yours could be probably formalize as much math as you can, as fast as you may. And mine is report as much as you can about your failures. Because my goal is to understand what is not easy to do in Mathlib and what is easy to do in Mathlib. And I've been through this path that allows me to be there. And as a practitioner of Mathlib, the way I do stuff, unfortunately, is rather to use brute force and say, okay, I know how to do that. It's painful, it's not interesting, but let's lose 10 minutes of our time. Maybe we should stop losing 10 minutes of our time and have 60 minutes of reflection of how the system should be built and sometimes. So you see, the goal is to have, I don't know if there is a pointer here. I try to this. The goal is, Mathlib is a formalized mathematical library, and it's a monolithic one. I mean, it's everything is there, or should be there, or will be there, or has a possibility of being there. And it's complicated to build a current mathematical library of that size. It's complicated because there are issues of choices, of and so on. So it's a point where my colleagues and I dissent. So I will make absolutely no use of large language models, whatever they could bring. And my scientific point of view is that they don't solve the problems they claim to. And for a reason, because they are, as explained in the paper by Emily Bender and her co-authors, they are stochastic parrots. And I need, as a scientist, a proof or an indication that a scientist parrot could help for reasoning. And I don't see no such proof for the moment. And there is, I should have recompiled the thread, but there is a guy, a computer scientist called Jason Morgan, and they say that what makes them work is our ability or tendency to view faces on toast. So there is also a political point of view, and I hope the ICE won't come to take me that these technologies require amounts of energy that are totally disproportionate to the use, metals, water, and so on. And my personal belief is that these tech companies that promote them are threatening humanity. So I wish to keep away from them, and nobody shares their view, and we are adults, and we can probably agree to disagree. But okay. So now.
And also, they're unethical because they steal other people's.
Yeah, also, which is not, which is something I didn't write on the slide. But I have to admit, I should not, but a lot of people, a lot of mathematicians have stolen something from people. For example, there is this stuff called library genesis, which is extremely useful to mathematicians. So, and who has never shared a PDF file should throw me the first stone. So UFD. I'm probably going too fast, but then that's okay. The first 4 chapters of the book, Island and Rosen, cover these 4 topics. So the first one is called unique factorization, and it's essentially about integers, but sometimes about Gaussian integers, Z of I, a bit of Eisenstein integers, which are maybe explained, and polynomials over a field. There is a second chapter, which is a very different nature. It is applications of unique factorization. And in fact, it goes towards infinitude of prime numbers. And the prime number theorem is evoked. And the Chebyshev theorem is almost proved. I mean, lower bounds for number of prime numbers. The third chapter goes back to very elementary stuff about congruences between integers. And the fourth is interesting for me because it's about units in Z mod MZ. And last week, Mathlib didn't know about that. So, so the 4 chapters, they cover more than, they propose a lot of exercises. And some of them are already in Mathlib in some form. Some others are not in Mathlib, but they would be very difficult to put in Mathlib with the present state of the library. And it remains a lot of them that we can do something about. And I've tested that at least 30 exercises are doable. But it took me 1 week to do the 30 exercises. So, well, you're more than 30, so maybe. Okay, let's do a bit more math. So in the first chapter, there is unique factorization, as I said, and there are 4 rings. Z, K of T, Z of I, and Z of omega. And it happens that Mathlib knows about these 4 rings already. So this morning, we have seen the natural numbers. So and we have seen at some point, we have seen rational numbers, and we have seen that rational numbers are defined through integers, so Z. So, and polynomials we have not seen, Gaussian integers neither. And when I wrote the first version of my slides, I thought that Lin didn't know about the Eisenstein integers, but more or less it does. So what about integers? So here they are. So I have to launch something else, and since I was late, I did not prepare it, but that's okay. Where is my... So you see, I'm not using VS Code, but that's, again, everybody is free. So can you read? Is it? No, okay. So probably I should, I will zoom in and probably put it in. Is it better? Okay. Is it better?
Perhaps one step larger.
Yeah. Does it really go larger? Yes. Yeah, it does.
That's perfect.
That's good. Okay. So the import Mathlib is the same as this morning. Usually, when you do an actual Mathlib project, you want to restrict the stuff that you load, but for us, for the moment, it's not necessary. And then I just wanted, so I will make discussions in a slightly different way than Alex. For example, I want to discuss about what happens when we say hashtag check. So check, it asks the machine what is the object that is on the line. So what is Z? And Lim tells me Z is a type. So in fact, Lim builds on type theory, which is not exactly the same thing as set theory, in which we are used to formalize mathematics. And in type theory, objects have a type, some label that says that it's an object of this nature. And natural numbers are not integers. They are not rational numbers, except besides 1. But of course, we know that 0 can be viewed as a natural number or an integer or rational numbers. And so there are maps between those. But when you see that Z is a type, we don't see that it is a ring. It's a type, and probably it's hard to give another object. But so everything is a type. So it says so. There is something that says that ring that Z is a commutative ring. So it's the stuff called check inscom ring. So if I wanted to know why is it a commutative ring, I would have typed example. So give me a proof that it is a commutative ring. So it's com ring in this, and I type Z, and then I want a proof of that. And the way I can get a proof, if it exists in the literature, is asking Lin to give me the answer, and now it works, and he gives me apply question mark that it is int inscom ring. And so, sorry. So now I need to go there and type here. And so now we may want to see what is this inscom ring. It's there. So it's another file. And you see, it says that there is, it's an NatCom group already, that it's also a semigroup. And this is for multiplication, but it's hidden there, that there is something like 0 times something is 0, mul 0 is something like something times 0 is 0, and many axioms. Also, many stuff that you wouldn't guess are there, like the fact that there is some power map, which is built in the machine, and there. And it's called instance. That means that Lin, whenever you label something as instance, this morning we have seen def, theorem, and example. So example, it's forgotten as soon as you finished it. But def and theorem, they stay in the machine. And so when you define something as an instance, it will be in a big database of stuff, and when Mathlib needs them, it can take it automatically out of it. Of course, this can be complicated, because if you take a type Z, and you say, okay, I will define another ring structure on Z, and I put 2 instances, then Mathlib will 1 time over 2 take the first one, and the other time takes another one, maybe, and then it will be very confusing to prove any theorem. Because imagine that you want to prove A equals B, and in the right-hand side, it's one group structure, and the other one is another one, and you won't be able to be improved. So one has to be very careful when one enters an instance. And so you're not authorized to do that unless you're a master or you're asked to do. But,
it's like mathematically, if you put 2 different topologies in the same space and you're trying to prove
exactly. And then
which topology do you want?
Yeah, exactly. And there is one principle that you see when you do math, a lot of stuff are implicitly under the right. You say this map is continuous from R to R. And okay, there is a topology on R, and we've all agreed on what it is. And we don't want to repeat the topology at every time. Sometimes you want to put the discrete maybe on the left. And then there are ways to to state explicitly that you will put the discrete topology, but we'll ignore that for the moment. Okay. So the ring of polynomials, I said that it's k of t, or k of I use t as a indeterminate, but in Lean it's x. We will see. So I have to introduce stuff, which is a k, and because k, if I forgot this line, I type what are the polynomials with coefficients in k. The answer is I don't know what k is. So there is this stuff variable that says, okay, from now on, there exists something called k, which is a type. And there is this stuff, field k, that says that k is a field. And whenever you see plus or multiplication or minus, it will be referring to this structure of field. Yep.
I'm used to it now, but one question that always came to mind when I was starting is, wouldn't I just like to say k is a field?
Okay.
You can delete k of type. You can just say assume what's k is.
Well, I wouldn't.
No.
No, I would like to type.
So k is a field.
K colon field.
Okay. This could be possible.
But field is not a type.
That could be a type field. Yeah, that could be a type field. But
the problem is it forces you to make a choice. Like if you want, like, then the real numbers are either a field or a group or a ring.
Yeah.
So for composition.
So yeah, exactly. So if you say R is a field and it's a type field, then you would need a map from rings to field when you want to. But you don't have a map from field to rings. So yeah, yes, you have. So okay, you could have some coercions at the level of types, but well, it was a design.
Like reflecting how we actually use math.
Yeah, but I'd say something. I said something before. Your first question was, why don't we say that K is a field? Yeah. Because saying that K is a field gives no information at all. Because it doesn't say you what is plus, what is minus, what is multiplication. You aren't a field if you've not said what is 0, 1, plus, minus, and multiplication. So in math, we are used to say, prove that this set is a field. And this statement makes no sense. Because there is implied something that you will take this plus, this minus that comes from a very obvious place, a very sensible choice. But
you say the quintuple k with the function plus, with the function multiplication, with the specific.
So you could say that.
Yeah.
But your friend probably will say that it's a sextuple with a 0 in the second place. And so your fields won't be her fields. So the tuple definition is also a nightmare. But in some sense, yeah, this tuple definition takes care of this problem. Okay. That a field is not, you're not a field by yourself, you're not a field with a certain amount of data. And we'll see this stuff about data later on. So now, once K is introduced by variable, and I've said that K is a field, and in bracket, because it's the way instances can be summoned.
Yeah, but what does the square brackets mean?
It means that it will be used in a special type of hypothesis, like instances, like things you don't want to tell explicitly. For example, if
this object will probably have a plus in the multiplication and stuff, and now Lean knows that.
Yeah,
I wrote it in the
exactly, brackets. And all assumptions of kind field are given in that way. And so now I can check that polynomials are fields, polynomials exist. So now I have polynomial K. And I could wish to know that polynomials are a commutative ring. And it gives me a polynomial com ring. Showed me that this showed that it is also.
Exact. Where does it say that it is?
Because it suggests me to try this. And so there is this bi-exact, but bi-exact is the same as, oops, sorry. I could say just it's this. It's essentially equivalent. So there is this function, polynomial com ring, that defines a structure of commutative ring on a polynomial. I said that you see that it's written R of X here. And there is something that says that, okay, it's a com ring because it's a ring. And this is proven by polynomial ring. And it's also multiplication is commutative by some function which is somewhere else. So this syntax is very confusing because on the left-hand side, mulcom is the name of the datum that says that multiplication is commutative for polynomials. And the right-hand side, mulcom is the name, will I say, of something which is that says that, oh my God, that says that in a commutative magma, two elements commute. And so probably before that, there is a lemma on instance that says that the polynomials form a commutative magma. But I won't go that far for the moment. I'll play with that a bit. And you see, we could say k of x. So if I try to check k of x for the moment, it doesn't work. X is unknown. But there is this strange syntax that you can say, okay, now I will use polynomials, and I want to use all the simplifications of notation that is useful for polynomials. And then I have k of x, and I have also the fact that it's a commutative ring.
Wait, so it just wrote the type because, as
Yeah,
I said before,
exactly. It says that it's a type, but it exists. It's an object in the library. So now we could say introduce polynomial by take p in k of x and. Okay.
Sorry, so
yep.
This is after you introduce polynomial, and then you like give it the usual notation, or you define like I'm not.
No, it is this line open scope polynomial that says now use the notation for polynomials.
I use k.
K is introduced there.
Yes, but where did you define k bracket x to be polynomial?
Here at this line, for example, here. When it is this line, open scope polynomial, that says use the notation.
That doesn't have any notation in it.
Sorry?
That's a place in the math.
It's in the library.
Yeah, it's in the library.
So he's importing something from the library.
Okay, so
call that t, for example, kt.
I cannot do. If I want to use t, no, I can't. Yes, I can, but okay, the x is, so it. I could try to explain something.
So you already know that this is the only notation you can use for
polynomial. Exactly.
So that's kind of additional knowledge that I.
Exactly. No, that's why that's very good that you ask a question. So we introduce a notation that is prepared. So I could try to go there. No, not there. Sorry. Maybe there. Okay. Here there is a structure polynomial which is defined here. So we don't take well, I can say, okay. So polynomial, you see, it depends on a type, which is called R, which is assumed to be a semi-ring. That is, you have plus multiplication and some distributivity, but you don't have necessarily a minus. And there is something which is affine sub. So this is very subtleties of Lin, but it's an add monoid algebra on the integers. So that means that we take the monoid, the additive monoid, n, and we take the algebra of the monoid over R in the same way that you are probably used to take the algebra of a group. Yeah.
Linear combinations.
Exactly. That's what will come out at the end, but it's written like that. And so there is a full theory of what one can do on add monoid algebras in general before one even starts to do polynomials. It's the way stuff is introduced. Of course, in first year university classes, you don't do that way, unless you wish your students to leave and to go to other instructor. But okay. And so now I want to go back to the line. So polynomial is defined there as this, and just after that there is scope polynomial notation that says that whenever you type something. And just after that, bracket x bracket, it becomes a synonym for polynomial R. And here, there are no spaces between the quote and after the quote at the end. So it means that you are not authorized to put a space just after that. And if there were a space there, you would force probably to use a space. And if you wanted to use your polynomials as between, although I cannot modify the file, but between r minus, you don't say r of x, but r of t, you put a t instead of the x, and then you have another notation for polynomials.
You could copy these two lines and
Yeah.
paste them into your file
Exactly.
if you want, because you can't modify this one.
Let's try
You
that.
could just give yourself another notation.
And also with that X there, it's not going to give you any like other syntactic help, right? It's just a shortcut for saying polynomial R, or does X actually get other special syntax?
There's no R, so K. Yep.
So now I can listen to your question.
The way that that notation is defined there, is that giving you anything else that you can do with that symbol T?
No, no, exactly, no. So later on, there is a function called, I can choose, I can check polynomial.x, it's a name. And polynomial.x, it's a map that goes from, so implicitly on the right, you have the type of the coefficients, the assumption that the coefficients form a semi-ring, and then it gives you a polynomial.
Oh, that's like the injection of this.
Yeah, exactly. Exactly. That you'd get a.
You can also do like example of type K adjoint T, and give it x squared plus 1 or t squared plus 1.
No, so x squared.
Type K adjoint T. The type is.
Yeah. Okay. No, but then.
K adjoint x, and k squared plus x. Does it take it by exact?
No, what happens? It should work. Okay, so it doesn't work because I need to type polynomial.x.
You can open polynomial.
Yeah, I will, but I will show it in. So now you see it's painful to type polynomial.x all the time. So you can say, okay, whenever you see something that might make sense if it begins with polynomials, please fill in. And now I can define polynomial x2 plus x. Okay.
So now x.
You need a non-computable. Oh no, it's not a def. So it's a.
Yeah, it's a def. So it's implicitly it's a def. No, but I explained that. Yeah.
So I guess for with x, both the R and the instance are optional, and so that's why you can use x by itself as a variable.
Exactly. So the fact that we have curly braces here, it means that we don't explicitly write the field of the ring of coefficients all the time. It will be painful. And of course, sometimes it's difficult to understand. Lin cannot. So this morning we have seen how Lin can understand that epsilon has to be a real number after some work. Sometimes you write down a polynomial and it's not clear what the field of coefficient will be. And then Lin will complain. For example, if I write an example that for all, no, what could I write? But well, let's try x minus x is 0. And you see what happens. There is a complicated error message that says that there are meta variables that I couldn't understand. And it's very bizarre because it couldn't understand. So you see, he wants a subtraction between something that for the moment is called 6026 and something which for the moment is called 6164 and of t. So implicitly at that point, Lin thought, I need two semi-rings, R and S, and now a subtraction between polynomials over these two semi-rings so that the statement can make sense. And I couldn't, so there is a complaint.
But if you coerce the first x into k adjoint x.
So for example, I could take z of x. And the second one, so here it's okay because, so Lin said, okay, I need a subtraction and I have a subtraction between polynomials with z and polynomials in z of the z of x. So and so probably this z here, you will see that it is a polynomial. Oh no, we don't see it. So maybe here. here we see that it's a polynomial. It's z of t because the last notation that was introduced is used. But x is x because x is polynomial dot x and there is no polynomial dot t that has been introduced. So we should delete this notation because it will add some. So those are comments. But also I could say, okay, I want the difference between this between the polynomial x. Oh my God. So then, okay. So I take the polynomials x in z of x minus the polynomial x in n of x, and I want to do the difference, and Lin cannot do that by itself. And probably that means that there is no way in Lin that if I have a polynomial with integer coefficient, natural number coefficient, I can view it as a polynomial with integer coefficients, which is probably.
We should have that query.
I don't know, but probably that's if somebody could keep a note. Probably we should have this.
Now what you did is said, okay, first think about x as a polynomial with the
Exactly.
integer coefficients, no negative, and then like, okay, think about it in the bigger thing. That's the notation. Like,
yeah.
Okay.
So this means take x in this one. So what x is an abbreviation for polynomial.x that requires a semi-ring. So I say, okay, take n. By saying this, the machine will understand that it has to be n. And so now I say, okay, take this polynomial in n of x and try to view it as a polynomial in z of x. And the question is, in Mathlib, is there a map called a map of the type called coercion maps that goes from n of x to z of x? And apparently there isn't.
What happens if you replace t by k and forget about x?
So let's try another example. So you wanted z for the first one?
No, kx.
Kx minus what?
Just minus x.
I'm saying both have been k.
And zero also, zero is going to be a polynomial.
And 0, okay, 0 is a polynomial. And so it's not this, the 0 of the structure value. So the question is, for example, could this x could be a polynomial in natural numbers, or no, not at least integers, and not.
Can you replace the x by some other polynomial just so I have like.
It asked me to prove that x minus x2 plus 34 is 0.
Is it possible to
That's
embed
what
z
it
into
asked
k?
me to prove.
Yeah, okay, so.
Wasn't the proof?
No, there is no proof.
That was a claim. It's maybe true, maybe not in the context.
Exactly.
This
So
claim is not true.
we have seen something this morning. We have seen the arrow, the right arrow. Use the right arrow.
Right?
This one.
Oh, yeah.
Oh, which is this arrow. We have seen it in two contexts. We have seen it for sequences, because the sequence was written n to r. And we have seen at some point in an implication. So the great virtue of type theory, about which set theory is totally lacking any insight, is that we use the same framework to make the statements of the theorems and to make the proofs and to talk about mathematical objects. In type theory, a number, a statement of the theorem or a proof of that theorem are on the same footing. And when we define a theorem, when we state a theorem blah, 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 we have defined a type. And when we say colon equal blah, 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 or blue, 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 usually it's not the same, it's an element of that type. So a statement is a type, a number is a type, and a proof of the theorem is a type, and it has to be a member of the type described by the statement of the theorem. And everything is on the same level, and that's very practical for proof formalization. That's why computer scientists use that a lot, despite the fact that not all computer assistant programs, proof assistant programs use type theory. Mizar, for example, is using set theory. Okay.
Can you fix a copy of C inside of K in the real life CX?
So probably we should try to see whether there is a map from Z to K. So it said no, but if there is a map, probably there is a better map than just a map. A map from the integers.
Would be a morphism like with more properties in that.
Exactly. So the map you expect to have is a ring morphism from Z to K. So we have to ask about a ring morphism. So a ring morphism exists, of course, and it has a notation which is a map compatible with plus and multiplication.
Oh, wow.
This is a notation again, huh? And now it guesses something called in-cast ring home. Okay, that means okay. And so, but don't try to type euro star plus because it's not an arrow compatible with the graph. It's really a notation, and don't try to put a space or whatever. Okay. And so,
I am lost at this point.
I'm sorry.
Is K just a symbol that's been defined as type field? It has no elements. It has no structure.
Yeah, it has some elements.
It has elements.
Of course.
0 and 1.
Well, I mean, maybe it's just a symbol representing that you could have instances of that will have all the structure you need. So all those instances will have 0 and 1, but the symbol, I'm thinking it's just a symbol at this point.
The assumption that K is a field,
Yeah.
one of the hypotheses there is that there is an element called 0 in the field.
But does K actually have elements and addition and multiplication?
Yes.
So you've given all of that, but when you say K, you just said.
But when you start so if you do a differential geometry, you don't start like let R be a field because R is given. But when we do algebra, we start by let R be a ring. And then when you do that, you have 0 and 1, maybe -1, and 1 plus 1, and everything you can build with it, but you have nothing else. Well, we have implicitly a lot of stuff.
What are the names of the elements in K?
But what is the name if I say let R be a ring? What are the names of the elements in R mathematically?
I think I can.
A.
Let me try to answer this a different way. When you define this variable K, K is on the same status as the K inside a theorem that begins let K be a field, but somehow you've put it in the scope so that it applies to this.
Okay, so
Can you click through the definition of field?
yeah. So I wanted to answer. I'll do that, but I wanted to say, for example, let's imagine that we are in the field K and we want to prove something involving two elements of K that we'll call A and B. And I want to prove that maybe A plus B minus A minus B, put spaces, is A squared minus B squared. It's not a marvel. So first, of course, I won't prove it because I hope that it exists. And it exists. And it's called, it's fun to type. It's this bizarre stuff because there is square sub square AB which exists, but says that A2 minus B2 is A minus B, A plus B times A minus B. So the proof that was found is take this proof that those two stuff are equal and put them, take the symmetric. Okay. So here, but what I wanted to show is that now the context that I have on the right, I have my type K, which is something. I have the information that K is a field. It's line 2 here. And I have two elements, A of B and K.
It doesn't really have any elements except maybe 0 and 1.
It could have.
You could
It could be
You
F2.
can label elements and then you can operate on those
Exactly.
labels by using the rules of K.
But K could be F2, the field with 2 elements, and then you could have 25 levels and they would coincide, but that's it. Exactly. Well, sometimes people care about. Okay.
But then when you might want to give an example of K, and then you would have to give all that structure. For example, when you say the integers, hidden in there is all the structures of addition and multiplication.
Yeah, so that's what the map, where is it?
Well, you're about to tell us about Gaussian integers.
Yeah.
Yeah.
So Gaussian integers, so if we check what it is, just say that it exists. Of course, if you don't know the name Gaussian integers, you're stuck. If you don't know that Mathlib has something called Gaussian int, and that mathematically represents the Gaussian integers,
I couldn't take polynomials over the integers.
you can define them, but then you have to do the whole job. Okay. And maybe we might look at what are Gaussian integers, because if you do it like that, so you take z of x mod x2 plus 1, which you can do, you will need very quickly to prove that any element is represented by only two numbers, and it's a plus the class of a plus bx in a unique way, and use that systematically. So Gaussian integers actually are defined like that. Oh no, I'm sorry. So the thing is defined in a more general way. It's defined as take the square root of minus d, and it will be -1. So I'll have to go to what is square root d, and square root d is a structure which has 2 components called real and imaginary, whatever they could be, because d could be 2, so wouldn't really be an imaginary part, it would be something, but it has 2 components. And here that's the definition of the structure. Here you have the notation with the third. And then there is a lot of theorems which you don't want to have a too close look, but you're happy that people wrote them. That say that if you have an integer, you can view it as an integer or as a Gaussian integers, and whose real part will be the element and imaginary part will be 0, that you have a 0, which be the integer 0, that's the real part of 0, that you have a 1. So that means that now there is a 1 in the Gaussian integer. So we can't see because, yeah. So, yeah.
Strange, because when you defined the Gaussian, I thought when you define the Gaussian integers, don't you define it as you don't define it as a ring, you define it as a set.
Exactly. So I wanted to reach that part, but I wanted to show specific elements. No, but we have to navigate between. It has to be like that. So now I go again to square root d, and if I go later on, here there is an instance, so something that Lynn will remember all forever, that it is a not congruent. So sorry, so the plus has been defined somewhere else. Where is it? I missed it. Oh, okay, here. Here there is an instance that there is an addition, and the addition is given by, it's a function that take 2 Gaussian integers or element of square root z square root of d, and you have to define the real part of the sum and the imaginary part of the sum. And as you can guess, the real part of the sum is the sum of the real parts, and the imaginary part is the sum of the imaginary parts. Try to remember this in 10 minutes when I reach the Eisenstein integers.
Like, suppose I wanted to do the other way, just to introduce notion of ideals, or like.
What do you mean you want it the other way? You have to speak a bit louder, I'm sorry.
It was answered already. I wanted to ask whether it's possible to also define the Gaussian integers by the usual quotient way.
So if you do that, mathematically it will be perfect. But at some point, you want the machine to know that 1 plus I times 1 minus I is 2. If you do your way, you have to make the multiplication as you have to lift I and to a polynomial. So you have 1 plus x times 1 minus x. Observe that it is 2 plus x2 plus 1 or something like that, or minus 2 plus, and reduce. In this way, the machine can just make the computation by itself and tell you that it is true.
This is sort of like more of a software engineering decision.
Exactly.
Mathematical one.
But the goal is to have the machine make all the computations that you don't want to do when they are very automatic. It's the same with the statements of theorems and so on. We want to be freed from the basic stuff to be able to think about math. Except that for the moment, I have to tell you about gory things. Okay. And so you see that there is a negation in the Gaussian integers or whatever stuff. So that means that in Mathlib, you can have a structure with a plus, with a negation. That means you just have, if you have A, you have minus A, and you have no relation between the plus and the minus. At some point, there will be eventually actions that relate them and show that minus gives rise to subtraction and so on. But okay. And later on, so here there is a proof that there is an instance that it is an outcome group. So they say that, okay, we'll take the addition as the one that has just been defined before, and the 0 as the 1, the sub as plus minus b, and a negation as a negation, and blah, 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 and the rest is. And there are some theorems that are, you see, this stuff means don't prove it. This is not yet proved. It's like, sorry, but it's just that wait a little bit, try to fill the rest, and then at the rest, well, you here, you are stuck with 1, 2, 3, 4, 5 statements to prove, which are associativity, 0 plus an element is 0, an element plus 0 is the element, minus a plus a is 0, and a plus b is b plus a, commutativity. And the proofs are basically, it's very impossible to read because you have the same, everything is written at the same time. So basically, we do intros. That means that we introduce variables, as we've seen this morning, but we don't write names. That means that the machine gives you names that you can access. You can't access, but they have names. A dagger, B dagger, C dagger, blah, blah, blah. And now you've seen the statements have been replaced. There is no quantifier, but they have actual names and statements. And now these symbols mean try to prove everything at the same time. So there is a next that says, okay, 2 numbers are equal by this x if and only if the real parts are equal and the imaginary parts are equal. So the x says, okay, now you have to prove that the real parts are equal and blah, blah, blah. And against this symbol to say do that all the time at the same place. And now you have 10 goals to prove, because there were 5 theorems, and twice, one for the real part, one for the imaginary part. And there are 2 functions called addCom and addLeftCom, which have been defined a bit earlier, and I won't go there. And simp tells Mathlib or Lin, use these functions and combine them in every way you can to prove the results. And fortunately, at the end, there are no goals. If I had been the one who typed this at the first time, at least, and probably the person who typed this at the first time, really gave the proof of all statements. And just observe that the proofs are identical and try to use this complicated syntax to have 3 lines, which is not really necessary for Mathlib, but it's sometimes interesting that boring parts are something that can be automatized. Unfortunately, it's difficult to predict when you prove such a theorem how you can do that. So usually we do long proofs and then we shorten them. It's called golfing. I know that golf is a very important activity of some people in the States, but also in Mathlib. Okay.
A question.
Yeah.
So we have that notation $?_.
Yep.
So when you write just underscore, it tries to automatically synthesize whatever belongs.
Yeah. And if you type underscore and the machine cannot fill it right away, it gives an error message.
Yeah.
If you type $?_, it says, okay, I wait for later, and if I can't fill it at the end, I ask the user to provide the proof.
And then the proof becomes a new goal.
Yeah.
That's how we got 10 goals.
Exactly, 5 at the first time, and 10. Okay. And so now I'll finish on time. So the field of Eisenstein integers. So so here it's even more complicated. So Gaussian integers, I had written them as z of omega, and omega is a cube root of unity. So in Lim, we have seen z of square root of minus g. So I said, okay, I square root z of square root of minus 3. But it's not, because cube root of unity is -1 plus I square root of 3 divided by 2. And we don't have divided by 2 in z. So, so in fact, there is square root of z of square root of minus 3. And we need something else because it doesn't fit our needs. For Eisenstein numbers, which would be q of square root of minus 3, it would be very good, but it's not good for us. That's it. That's it. I mean, that's right. So fortunately, people like maybe Filippo and Ricardo Brasca and some other studied a lot about cyclotomic extension. I mean, rings generated by roots of unity, and there is a way to phrase this. So it's even more complicated. So we can say, okay, I will introduce something which is called a type K, and it will be a field. It will also be a number field, which means that it's a Q algebra and finitely dimensional. That's hidden in the way. And we assume that it is a cyclotomic extension for the number 3, or the set of number 3, relative to Q and K, which means that it's obtained by adding to Q cube roots of unity. And we can go to the definition. And is cyclotomic extension, you see, it depends on a set of integers, some algebra and some type, some other type. The first one is a comring. The second one is a comring as well. The second one has to be an algebra of the first one. And there is the assumption that there is a B has primitive roots of unity of each order requested by the set S, and that those roots of unity generate the algebra. Okay, so that's the way we can frame this in Lean today. And then when we do that, we have the ring of the field of Q of square root minus 3, in fact. But now this is the number field, and I can take about this ring of integers, which will be the correct ring. But at this point, it's not clear that any element can be written in a unique way of the form A plus B omega. Well, we could find something, and that the multiplication is given in the way you want, and that if you want to prove equality, you just check the real and imaginary part. I mean, 2 coefficients, and decide equality at once. Okay. So there is, for the moment, I know there is a project of defining more general stuff like Gaussian int, or z of square root of minus d, where you also write this not only a polynomial x2 equals d when you add or equal minus d or whatever. No, x2 equals d, but x2 plus x plus b equals 0. You add the root of degree 2 polynomial. And that would be very practical because we would have very concrete Eisenstein elements. Okay. And for this reason, I didn't even try to solve the exercises of Island and Rosen about Eisenstein because they would be complicated. If we think about the proofs we do, it's really by writing them A plus B omega and things like that. And so it needs something. So the last thing I want to show, and then it would be time to close, is what does it mean that there is unique factorization? So maybe I wanted to show something. Why is the stuff? So here I've just talked about that for. So yeah, okay. The titles of the slides are only for Alex. So in every ring, there is a notion of being multiple, a notion of divisibility. So automatically, well, and these notions are being implemented in Lean, so in Mathlib. So automatically, Mathlib will be able to talk about divisibility in those rings and units in those rings and so on. Probably there will be non-theorems, like Mathlib knows that the units in Z are plus or minus 1. Probably knows that the units in Gaussian integers are 1 minus 1, I minus I. Certainly, or maybe knows about the units in the cyclotomic for Eisenstein integers, because they've formalized the Fermat's last theorem for 3, so it should be there. And there is a notion of primes. So primes is defined by you're not a unit, and if, well, no, sorry. I'm sorry, I'm ashamed. So it's not the definition of primes, it's the definition of irreducible, and there is another definition of primes. Okay. So, and unique factorization means that up to units, every non-zero element can be written as a product of primes in an essentially unique way. If you try to reflect of what it means, it's a bit complicated. Especially, I took some time to write up to a unit. Because if you take an element which is a unique, you will write it as an empty product of primes, but then it will be equal to 1. So you have to put a unit in front. And if your elements are not units, you can put the units in the primes, and so it's complicated. And then you have the ordering, you have to reorder and multiply by units. And so it's a bit complicated to state explicitly. What I want to say mathematically is that in these 4 rings, they have unique factorization for a reason that they are principal ideal domain, and for the reason that they are Euclidean rings. That means they have a Euclidean division. For integers, the Euclidean division has been defined by Euclid. In fact, no, the Euclidean division has been defined for natural numbers, but we say that Euclid did it for integers as well, which is, it can't be true because Euclid didn't know about negative numbers that did not exist. I mean, and Lean Mathlib doesn't know that the ring of Eisenstein integers has a Euclidean division. It only knows that it is a principal ideal ring. So if I go back to the stuff, if I hope I can find it again, no, it's there. So I'm introduced a new hashtag, is hashtag synth, just because it was simpler to show. So when I write this, I say, do you have an instance somewhere that this is true? So it means synthesize. So give me so unique factorization Z, and so Lean answers that Z is a unique factorization monoid because it is the way unique factorization is stated. So in Lean, you have monoids and you have admonoids. Monoids, the law is multiplication. Admonoids, the law is addition. So if I take Z, the law is multiplication. So saying that it is a unique factorization monoid, it means that it is for multiplication. Okay. And unique factorization is not only for monoids, it's also for probably something called cancel come monoid with 0. So these are stuff that are monoids, that are with 0. They have a specific element 0. And there are cancel monoids. I mean, you can cancel by everything which is non-zero. And all of this has been, all this stuff which are not belong to the nightmares of every single mathematician are necessary to be put in the library so that we can state everything only once and not multiple times. Okay, and now why is Z a principal ideal ring? Because when you do that, you see, I want to show this. You see, that says that you are a unique factorization monoid here on the right. If you take Z, you ask that it is a com ring, you ask that it is a strict order ring, and it means that it has an ordering and which respects strict inequalities, and it's supposed to be a Euclidean domain. And so, in fact, Lin knows that Z is a Euclidean domain, and it's there. So you have the definition of a Euclidean domain. You see, it's very, again, it's very general. You say that, well, it has to be non-zero. You should have a division with a remainder. So you need to have two operations, slash and percent, and you need to have a valuation usually which is not natural number valued, but in fact in Lin, it's it's generalized because the only thing you need is that the relation given by the remainder and A mod B and B has to be well-founded. And in fact, you have papers from the 60s, one by Samuel, for example, that says that one could define Euclidean rings in this way, but it's not clear that it has any improvement from the mathematical point of view. But from the proof perspective point of view, it has an improvement. And also, if you say that the gauge function R2n, if you put it, then it's okay for natural numbers or integers, but it's not okay for polynomials. You know, it's slightly different. You have to assume that the degree of 0 is minus infinity if you want that it fits very well. And so if you've written n, you're not allowed, n is not n plus minus infinity. Okay, so it's very cool to have something. And also it's cool that the Euclidean domain does not really depend on the gauge function, but only on the consequence that you don't have infinite decreasing sequences. I mean, the remainders. Okay. And so what I wanted to show, now I need to, what happens? Okay. What I wanted to show is that, okay, being a Euclidean domain, contrary to being a unique factorization monoid or being to principal ideal ring, it has some datum. It contains the definition of the slash function, the division, and the remainder. Okay. So this has datum, and probably, okay. And now if I go to why are Gaussian integers a principal ideal ring, it say, okay, you see that it's Euclidean domain. It's because it's a Euclidean domain, and why it's a Gaussian. So there is a definition somewhere. I won't click. I want just to finish by showing why is okay the ring of Eisenstein integers principal. Okay, so it's fun. So I ask, do you know? I mean, when I say that, I'm asking Ming, do you know on the nose that the ring of Gaussian integers is a principal ideal ring? And the answer is fail to synthesize. It doesn't mean that nobody proved it, but it means that it's not on the list of the stuff that Lin can find automatically. It won't, there are millions of lines of code. It won't try to use everything all the time. But there is a theorem that says it. So if the theorem, if I try to do this, is principal and if I do this is how I
colon after example.
And it found it. So I mean, when I asked this, Lin said, okay, you want me to browse the library and to find something like that? I can do it for you. And it's relatively fast. I mean, it's amazing. And now, if you have a look at the proof of this theorem, so it's called is cyclotomic extension .rat.3PID. Okay. And if I go there is a theorem. You see the proof is quite short, but it does something that it applies the theorem that if the discriminant of a number field is smaller than some expression, then the ring of integers is a principal ideal theorem, something that calls from the Minkowski theory. And then the rest of the proof is compute everything and prove that it's okay. So you see you have two different proofs of two different natures. That means that computing with Gaussian integers will be slightly more complicated than it is with Gaussian integers. Okay. So I've shown you that. And now you're supposed to be able to do something by yourself. It will be a nightmare, but we will be there. I hope we will enjoy anyway. Thank you.
Thank you.
quadratic integer is always formalized in already, or is it something pending? Like integral closure of C.
Yeah, it's pending. It's probably pending because I've seen people discussing on Zulip about it, but I don't know the exact status. So this is the stuff. It would be very natural to do it, just to copy the file and to modify everything. But there is a slight possibility that somebody has done 90% of it already, and then it will be complicated. But it's something to do. I mean, so yeah.
I'm surprised that the list of Euclidean domains is not formalized.
Exactly. That's those are results that could be in the machine.
Do you have a plan for the afternoon for what should we do?
Okay, so I can show. I think here is island erosion. So I should push something on the lib just during the lunch talk. So so I was interested in the first chapter for the moment. And so you have exercises. So I can't comment on the first exercises, and maybe we could. So the first one is to prove Euclidean division. So of course it's not clear that there is something to prove because it exists already. And the book of Island and Rosen is very good on many respects, but very bad on some others. So here you have used this already. So why is it requested to prove it? But that's okay. So then there is a proof of the Euclidean algorithm. Okay. And
but just figuring out how to state that in Lean is a useful exercise.
So except that one is easy, or no, is reasonable. Two is not so easy. To prove that there is some sequence, so from two numbers you build a sequence, it will be complicated. You need to learn about how to define a function by induction, and it requires another class. So maybe I can devote a class in 2 days to do that, but otherwise it wouldn't be reasonable. So the three calculate something. Well, the function that computes the GCD of two numbers you can guess is int.gcd when the numbers are integers and not.gcds when they are natural numbers. And you could try #eval as we've done #eval 2 + 2 and check that you can get the answers. And then the exercise become easier. There is something funny with exercise 15, which is possible to do in Lean, except that it is false. Because it's not true that a number is the square of something if the periodic variations are all even. Yeah? -1. But okay, now in Lean, it's okay. We know that some hypothesis is missing. We plug in the hypothesis that the number is positive and go on. And okay, so there are some exercises that can be done. And what I propose is to push at least, I have a statement of maybe 21st exercise. I will push the list with stories, but I think we should discuss with us on the blackboard which are easy and which are not. Okay. Well, which are doable and which are not.
To get an idea.
But we need tea. Sorry?
To get a rough idea, what should we do for the rest of today?
So in 10 minutes, once I've got cold water, you will be able to download the file with statements of the exercises. I mean, Lean versions of those. And if you can't download it, you can have a look at the paper as this, which I could leave on the blackboard like this, and try to type clean code to see what you can do with it.
Thanks.
And anyway, we will pass through people. We are to help. It's
So between roughly 2:30 to 3:30, although we're late, so we'll have a good tea break. We can work on either these exercises or you continue with real analysis.
Yeah, I don't know.
Around 3:30, we'll come around and see which among you would like to present at 4 o'clock the things that whichever exercises you formalized and how you did it, so that others can see. And so from 4 to 5, we have a little show and tell where you guys can come up, just plug in and say, here's what I figured out how to do, and this is where I'm stuck, and we can give some comments. Okay, that's it.
And as I said in the beginning of the talk, it would be very interesting that you keep track on every of your struggles. My experience is that we forget about our struggles. And then when we write a paper about formalizing this stuff in Lean, we have nothing to say because we've solved everything and we forgot about everything we needed to do. But the important information now that we have formalization is not the proof. I mean, the proof, okay, now the machine says, okay, there is no sorry in the proof, it's okay. But it's how can we reach that? So what are the important mathematical ideas, not the boring stuff? And what are the important code writing ideas that were needed, which is a slightly different skill.
So do you mean we summarize from this machine proof in the original national equation?
So you describe where the difficulties were in coming up with the machine proof.
Oh, okay.
So, for example, even having at one place negative integers or an integers, and at the other place a natural numbers, and having Lean making trouble to conflate both notions in your formula, it's an important thing to observe.